In May of 1902, an archaeologist named Valerio Stias stood in the National Museum of Athens, holding fragments of corroded bronze pulled from a shipwreck. The pieces had been sitting in storage for over a year, dismissed as scrap metal by his colleagues. But Stias noticed something the others had missed. Through the corrosion, he saw the unmistakable outline of a gear, then another, and another. What Stias held in his hands that day would challenge every assumption about ancient technological capability. The Antikythera mechanism, as it would later be called, contained at least 30 bronze gears, machined with a precision that shouldn't have existed for another 1,000 years. The device didn't just mark time, it predicted eclipses, tracked planetary movements, and calculated astronomical positions with accuracy that modern researchers struggled to replicate using the tools available in 100 BCE. X-ray analysis conducted in 1971 revealed something even more disturbing. The mechanism used differential gearing, a technology historians insisted wasn't invented until the 16th century. The inscriptions covering every surface described astronomical phenomena in such detail that it took decades to fully translate them. Whoever built this device understood the solar system in ways that contradicted the official timeline of human knowledge. No other mechanism of comparable complexity appears in the historical record for over a millennium. No workshop, no prototype, no evolution of design. The Antikythera mechanism exists in isolation, a precision instrument that modern science can explain but not reconcile with the supposed technological limitations of its era. The question isn't just how they built it. The question is why no one built another one. But the Antikythera mechanism isn't alone. Scattered across museums and archaeological sites worldwide are instruments that demonstrate precision far beyond what their creators should have possessed. Each artifact stands as physical evidence of technological sophistication that doesn't fit the established narrative, and each raises the same uncomfortable question. What else did ancient civilizations know that we've forgotten or never learned? In 1936, workers excavating near Baghdad unearthed clay jars from the Parthian period. Nothing unusual at first, but when archaeologist Wilhelm Kigg examined them, he noticed something the laborers had overlooked. Each jar contained a copper cylinder held in place with asphalt. Inside the cylinder, an iron rod. The configuration was unmistakable to anyone familiar with electrochemistry. King proposed that these jars functioned as galvanic cells' primitive batteries. When filled with an acidic solution like vinegar or wine, the dissimilar metals would generate an electric current. Replicas built using the exact specifications produced voltages between half a volt and 2 volts. Not enough to power modern devices, but sufficient for electroplating gold onto silver or copper objects. Archaeological evidence supports this theory. Ancient gilded objects from the same region show characteristics consistent with electroplating, rather than the mercury gilding process documented in historical texts. The precision of the metal deposition suggests a controlled electrical process, not chemical application. Yet the historical record contains no mention of electricity or its applications for another 2,000 years. The objections came immediately from mainstream archaeology. Some claimed the jars held sacred scrolls. Others insisted they were storage vessels for mundane liquids. But none of these alternative explanations addressed the deliberate construction, the precise fit of the copper cylinder, the careful sealing with asphalt, the iron rod suspended without touching the cylinder walls. The engineering wasn't accidental. Someone designed these objects with a specific electrochemical function in mind. Multiple jars were found in different locations across ancient Mesopotamia. This wasn't a single craftsman's experiment. The technology was replicated, suggesting knowledge that was shared, perhaps even systematized. And then it vanished from the historical record, leaving only these silent artifacts and the persistent question. If ancient cultures understood electrochemistry well enough to build functional batteries, what other electrical applications did they develop? In 1936, the same year the Baghdad batteries were discovered, an entirely different precision instrument came to light in an Egyptian tomb. Dr. Khalil Messiah, examining artifacts from Saqqara, noticed a wooden bird model that didn't match other ceremonial objects from the period. The proportions were wrong for decoration. The tail was vertical, not horizontal. The wings showed a dihedral angle, slight upward curve used in modern aircraft design to provide lateral stability. Messiah brought the object to aviation experts who confirmed what seemed impossible. The Saqqara bird, dated to approximately 200 BCE, demonstrated aerodynamic principles that wouldn't be formally understood until the Wright brothers. Its 18-centimeter wingspan and precisely carved body produced lift when tested in controlled conditions. This wasn't a child's toy or a religious symbol. It was a scale model of a functional glider. The vertical tail stabilizer proved most controversial. Ancient Egyptian artwork consistently shows birds with horizontal tail feathers spread for display, but the Saqqara bird's tail stands perpendicular to the body, exactly as a rudder would be positioned on an aircraft. Some researchers suggested it might be a weather vane or a ceremonial scepter, yet the aerodynamic testing showed that this exact configuration was necessary for stable flight. More wooden bird models surfaced in subsequent excavations, though none as sophisticated as the Saqqara specimen. Some had lost their tails over millennia. Others showed cruder construction, but several displayed the same vertical stabilizer and dihedral wing angle. The question shifted from whether ancient Egyptians understood aerodynamics to how extensively they applied this knowledge. No written records describe gliders or flying machines in ancient Egypt. No tomb paintings show humans in flight. Yet the physical evidence exists, carved with precision and proportioned according to principles that modern aerospace engineers recognize immediately. Either this represents an isolated moment of accidental genius, or ancient Egyptian craftsmen possessed knowledge of flight dynamics that was never formally documented and somehow never developed further. The precision extends beyond individual artifacts. In 1513, Ottoman admiral and cartographer Piri Reis completed a world map that should not have been possible. The map shows the coastline of Antarctica with remarkable accuracy. Not the ice-covered continent that European explorers would discover in 1820, but the actual landmass beneath the ice, as it would appear without glacial coverage. Modern satellite mapping using ground-penetrating radar confirmed what seemed impossible. The Piri Reis map correctly depicts Bay's mountain ranges and coastal features that have been buried under ice for at least 6,000 years. Piri Reis himself noted in the map's margin that he compiled it from more than 20 source maps, some dating to the time of Alexander the Great or earlier. But this explanation only deepens the mystery. How did Alexander's cartographers or anyone before them map a continent that wouldn't be ice-free in any documented historical period? The mathematical precision of the map's projection adds another layer of complexity. Piri Reis used a coordinate system and projection method that closely resembles modern cartographic techniques. The longitudes are accurate to within half a degree, across thousands of miles. This level of precision requires not just skilled observation, but systematic surveying and sophisticated mathematical calculation. Scholars propose that the map shows South America's coast distorted by copying errors, not Antarctica at all. But the geological features matched precisely. Mountains appear where ground-penetrating radar later confirmed mountain ranges beneath Antarctic ice. Rivers flow from correct highland sources. The coastline curves match the bedrock topology hidden beneath 2 miles of ice. Either Piri Reis accessed source materials from a civilization capable of mapping Antarctica before glaciation, or the map represents a coincidence of errors that perfectly replicate features unknown until satellite technology made them. Visible in the 1960s, but mathematical precision wasn't limited to navigation and cartography. In ancient Egypt, construction and commerce depended on standardized measurements maintained with obsessive accuracy. The royal cubit rod, discovered in multiple tombs and temples, served as the fundamental unit of measurement for pyramid construction and engineering projects. These rods measured 52.3 centimeters, subdivided into digits and palms with precision accurate to fractions of a millimeter. Archaeological analysis of cubit rods from different dynasties spanning 1,000 years shows consistency that modern manufacturing would struggle to achieve without industrial equipment. The variation between rods averages less than 0.2 of a millimeter across specimens separated by centuries and hundreds of miles. This wasn't approximate measurement. Ancient Egyptian metrology operated on tolerances that demanded sophisticated calibration methods and quality control. The implications become clear when examining pyramid construction. The Great Pyramid of Giza maintains right angles accurate to 2 arc minutes across a base covering 13 acres. The four sides align to cardinal directions with error margins of less than 4 arc minutes. This precision requires more than skilled craftsmanship. It demands measuring instruments capable of detecting and correcting minute deviations across massive scales. How did ancient Egyptian craftsmen maintain such consistency without modern calibration standards? The cubit rods themselves had to be measured against something. Historical texts mention master rods kept in temples, but this only pushes the question back. What served as the original reference? Some researchers propose natural constants, the Earth's dimensions, or astronomical measurements, but no ancient text confirms this. The precision exists, documented in wood and gold and stone, but the methodology remains lost. While Egypt built with cubits, ancient China developed instruments for entirely different precision applications. In 132 CE, astronomer and engineer Zhang Heng presented the Han Dynasty court with a bronze vessel that seemed to defy explanation. 8 dragon heads protruded from the sides, each holding a bronze ball in its mouth. Below each dragon, a bronze toad sat with mouth open. The device was beautifully crafted, but its purpose remained unclear until the ground began to shake. During an earthquake in Luoyang, one of the bronze balls dropped from a dragon's mouth into the toad below, producing a resonant chime, but no one in the capital felt any tremor. Skeptics at court questioned whether the device had malfunctioned. 3 days later, a messenger arrived from Longxi 400 miles to the west, reporting a devastating earthquake. Zhang Heng's seismoscope had detected the seismic waves, while the tremor remained imperceptible to human senses in the capital. The mechanism inside the bronze vessel has been lost. Modern replicas based on historical descriptions and surviving fragments use various pendulum and lever systems, but none have achieved the same sensitivity and directional accuracy. Zhang Heng's original device not only detected earthquakes at extreme distances, but indicated the direction of the epicenter by which dragon released its ball. This suggests a precision balance system capable of distinguishing minute directional forces. No comparable seismographic device appears in any other culture for another 1700 years. The technology didn't spread or evolve. Zhang Heng's seismoscope remained a singular achievement. Its sophisticated internal mechanism never fully replicated or explained in surviving texts. Modern seismologists acknowledge that the principle is sound and the reported performance is theoretically possible, but reconstructing the exact mechanism that achieved such sensitivity with Han Dynasty metallurgy and materials remains an unsolved challenge. Another form of precision existed not in metal or stone but in knotted strings. When Spanish conquistadors encountered the Incan Empire in the 16th century, they found no written language. Yet the empire administered a population of 10 million people across 2,500 miles of mountain and coastal terrain. The bureaucracy operated with efficiency that impressed even Spanish observers. The secret lay in the khipu recording system, using knotted cords that encoded information with mathematical precision. Each khipu consisted of a primary cord with numerous pendant strings attached. The strings varied in color, length, and material, but the information resided in the knots. Different knot types, positions, and spacing represented numerical values in a based-in positional system. A single khipu could encode census data, tax records, military supplies, and agricultural production with accuracy that allowed rapid auditing and cross-referencing. Recent analysis suggests the khipu system encoded more than just numbers. Patterns in knot placement, string color combinations, and spatial relationships hint at linguistic or narrative content. Some khipu appear to record historical events or genealogy. Others may contain instructions or procedural information. The Spanish destroyed most khipu during the conquest, recognizing them as tools of indigenous knowledge systems that threatened colonial control. The few surviving khipu demonstrate precision that modern researchers struggle to decode. The knot positions maintain consistency across different khipu makers, suggesting standardized training and quality control. An error in knot placement could falsify tax records or miscalculate military resources. The system demanded both mathematical sophistication and manual dexterity to create error-free recordings. Inca administrators who maintained these records underwent years of training, and their work was audited by independent khipu readers to verify accuracy. No modern civilization has successfully recreated a fully functional khipu recording system. The combination of numerical encoding, Color coding and potential linguistic content creates a complexity that exceeds simple binary computing in some aspects. The Inca developed this instrument over centuries, refining it into a precision tool for managing one of history's largest and most complex empires. When the Spanish conquest ended, the knowledge of creating and reading khipu died within a generation. What survives are artifacts we can count but cannot fully comprehend. Meanwhile, across the ancient Mediterranean, Greek engineers developed surveying instruments that made Roman engineering possible. The dioptra, described in detail by Hero of Alexandria in the 1st century CE, functioned as a combined theodolite level and measuring device. The instrument allowed surveyors to measure angles in both horizontal and vertical planes with precision sufficient to design aqueducts with gradients, accurate to less than 1 degree over distances of dozens of miles. Roman aqueducts demonstrate what this precision enabled. The Aqua Claudia, completed in 52 CE, maintained a gradient of approximately 2 meters per kilometer over a 69-kilometer course. The gradient never varied enough to cause flow problems or structural stress. The water arrived in Rome at a predictable rate and pressure, supplying fountains, baths, and public buildings with engineered reliability. This consistency required surveying instruments capable of detecting slope, variations of less than a centimeter across kilometer-long sections. The dioptra's design suggests sophisticated understanding of geometric optics and mechanical precision. The sighting tubes incorporated crosshairs for targeting distant reference points. Gear mechanisms allowed fine adjustments in both horizontal and vertical planes. A water level, or plumb bob, ensured the base remained perfectly level during measurements. The entire instrument could be disassembled for transport and reassembled with reliable calibration. Yet, for all its sophistication, the dioptra vanished from engineering practice after the fall of Rome. Medieval European surveyors relied on cruder tools like plumb lines and right angles. Established through rope geometry, the precision required to build Roman aqueducts and roads became impossible to achieve. The instruments existed documented in Hero's surviving texts, but the manufacturing techniques and calibration methods were lost. Europe wouldn't recover comparable surveying capability until the Renaissance reintroduction of Arabic astronomical instruments themselves preserved from Greek originals. Precision took entirely different forms in other contexts. Ancient Egypt's agricultural economy depended on predicting and measuring the Nile's annual flood. Too little flooding meant famine, too much meant destruction. The Egyptians built Nilometers precision instruments for measuring water levels with accuracy that allowed prediction of flood heights weeks in advance. The most sophisticated Nilometer, located on Elephantine Island near Aswan, consisted of a stone-lined shaft with precisely calibrated steps descending to the river. Each step represented a specific water level, with additional graduations carved into the walls marking smaller increments. Priests recorded daily readings, building a database of flood patterns that stretched back centuries. This data allowed remarkably accurate prediction of flood severity based on early season water levels. But the Nilometer was more than a measuring device. It formed the basis of the entire Egyptian tax system. Higher floods meant greater agricultural productivity and higher tax assessments for the coming year. Lower floods triggered tax relief and grain distribution from stored reserves. The measurement precision had to be absolute because the empire's economic stability depended on accurate flood forecasting and equitable taxation. The engineering precision required to build a Nilometer that remained accurately calibrated across centuries challenges modern assumptions. The structure had to resist erosion from annual floods while maintaining exact dimensional relationships between steps and graduations. The foundation had to prevent settling that would throw off calibration. Modern reconstructions of Nilometer function confirmed the mathematical sophistication required to convert water level readings into agricultural yield, predictions, and tax assessments. Records show that Nilometer readings were treated with religious significance, but the underlying methodology was rigorous empirical science. Multiple independent observers verified readings. Historical flood data was cross-referenced against current observations. False reporting was punishable by death because inaccurate measurements threatened the empire's food security. The Nilometer represents precision instrumentation applied to environmental monitoring with consequences measured in human survival. Across the Atlantic, Mayan astronomers achieved observational precision that rivals modern measurements. The Dresden Codex, one of 4 surviving Mayan manuscripts, contains astronomical tables that calculate planetary positions and eclipse cycles with stunning accuracy. The Venus table predicts the planet's synodic period, the time between successive appearances in the same position relative to Earth and Sun, as 583.92 days. Modern measurements using telescopes and atomic clocks calculate 583.92 days. The Maya achieved this precision through naked eye observation and mathematical analysis. The eclipse tables demonstrate even more sophisticated calculation. Mayan astronomers predicted both solar and lunar eclipses with accuracy that allowed precise ceremonial timing decades in advance. They understood the 18-year Saros cycle that governs eclipse patterns. They calculated the moon's orbital inclination. They accounted for the precession of the lunar nodes. Each of these astronomical parameters requires centuries of systematic observation and mathematical modeling to derive accurately. But the Maya lacked telescopes, photographic plates, atomic clocks, or computers. Their observations relied on architectural alignments, shadow casting, and patient record-keeping spanning generations. The precision of their calculations demands observational instruments we haven't fully identified or understood. How did they measure planetary positions accurately enough to detect Venus's slight irregularities? What instruments tracked the moon's position to the precision needed for eclipse prediction? Recent archaeological discoveries suggest the answer may lie in architectural astronomy buildings and plazas designed as giant observational instruments. The palace at Palenque contains sightlines that mark specific solar and lunar events. The pyramid at Chichen Itza casts serpent shadow patterns during equinoxes. These structures functioned as cylindrical and astronomical calculators, allowing observations accurate to fractions of a degree through careful architectural engineering. The buildings themselves were the precision instruments. The Dresden Codex represents generations of accumulated data compressed into mathematical tables. When Spanish conquistadors reached the Maya territories, they burned most codices as pagan texts. The astronomical knowledge, the observational methods, the calculation techniques all reduced to ash. The surviving codices escaped destruction by accident, not preservation. What remains demonstrates precision that modern astronomy respects but cannot fully explain given the supposed technological limitations. But not all ancient precision instruments have obvious purposes. Roman dodecahedrons, well-faced bronze objects with circular holes on each face, have been found across Europe from Britain to Hungary. Each face contains a circular hole, and the hole sizes vary systematically across faces. Knobs protrude from each vertex. The objects are beautifully crafted, requiring significant skill and bronze to manufacture. Yet no Roman text mentions them. No inscription explains their purpose. No artistic depiction shows them in use. Modern researchers have proposed dozens of theories. Some suggest astronomical instruments for calculating optimal planting dates. Others propose surveying tools, rangefinders, or candle holders. Some claim they measured water pipe diameters or served as scepters. Archaeological context provides little help. Dodecahedrons turn up in temples, military camps, urban centers, and rural villas without clear pattern. The one consistency is precision. The holes are carefully sized, the faces symmetrically crafted, the overall geometry exact. The most intriguing proposal suggests dodecahedrons functioned as light meters for gold testing. Different hole combinations would project specific light patterns, useful for assessing gold purity through color analysis. This would explain the varying hole sizes, the symmetric construction, and the expensive bronze material. It would also explain why Romans didn't document the device in writing gold. Testing techniques were closely guarded, trade secrets, but without confirmation from ancient sources, the purpose remains unknown. What's certain is that Romans manufactured these objects in significant numbers across a vast geographic area. The precision of construction suggests specialized knowledge and specific function. The complete absence of documentation suggests either extreme secrecy or a purpose so obvious to Romans that no explanation seemed necessary. Modern researchers can measure the dodecahedrons, replicate their geometry, and test various hypotheses. But the original function and the knowledge required to use them properly remains lost. Viking navigation represents another intersection of precision and mystery. Norse sailors crossed the North Atlantic to Iceland, Greenland, and North America without magnetic compasses, which hadn't yet reached Europe. Icelandic sagas mention a sunstone, a crystal that allowed navigation even when clouds obscured the sun. Modern researchers dismissed this as legend until optical physics suggested a plausible mechanism. Certain crystals, particularly Iceland's spar calcite, exhibit strong double refraction and polarization effects when rotated while viewing the sky. These crystals show changes in light intensity that indicate the sun's position even through thick cloud cover. The effect works because scattered sunlight in the atmosphere becomes partially polarized, creating patterns that calcite makes visible. A skilled navigator using a sunstone could determine solar azimuth to within 5 degrees accuracy sufficient for North Atlantic navigation. Archaeological evidence remained lacking until 2013, when a calcite crystal was recovered from an Elizabethan shipwreck. The crystal was stored with other navigation instruments, suggesting deliberate use for seafaring. While this dates to centuries after the Viking Age, it confirms that European sailors used optical crystals for navigation. The Viking sagas may have described an actual technique, not mythological symbolism, but identifying the sun's direction through clouds is only part of navigation. Vikings also needed latitude determination. Some researchers propose they used bearing dials, wooden instruments with shadow casting gnomons calibrated to measure solar altitude. At specific latitudes, the noon sun reaches consistent maximum heights. By measuring this daily maximum, navigators could determine whether they were maintaining proper latitude during Atlantic crossings. The precision required seems extraordinary. A ship rolling in Atlantic waves provides an unstable platform for precise solar measurements. Clouds and fog obscured the sun for days at a time, yet Norse sailors made successful crossings to North America around 1000 CE, roughly 500 years before Columbus. They navigated without losing ships to random wandering or failing to locate small island targets like Iceland. This demanded precision instrumentation and observational techniques that left minimal archaeological traces. The Viking example illustrates a broader pattern. Ancient precision instruments often survive as fragmentary evidenza mentioned in a saga. A corroded crystal in a shipwreck, a successful navigation that shouldn't have been possible. The complete technology remains elusive. We can confirm that sophisticated instruments existed and functioned effectively, but the full methodology, the calibration techniques, the training systems, the quality control measures disappeared with the cultures that developed them. This pattern of precision without documentation extends across civilizations. The Antikythera mechanism demonstrates astronomical computing capability that wouldn't reappear until mechanical clocks of the Renaissance. Baghdad batteries show electrochemical knowledge that European scientists wouldn't formalize until the 19th century. The Saqqara bird exhibits aerodynamic principles that aviation pioneers would discover through trial and error. Egyptian cubit rods maintain tolerances that demand industrial lira quality control. Zhang Heng's seismoscope detects earthquakes at distances that challenged 20th century instruments. Each artifact represents a technological peak that wasn't sustained or built upon. The knowledge existed, produced physical evidence, then vanished from the historical record. No evolutionary sequence leads to these instruments. No successor instruments show incremental improvement. They appear in isolation, function for a period, then disappear, leaving only the artifacts and the questions. Mainstream archaeology explains this through inevitable knowledge loss during social upheavals. Civilizations collapse, wars destroy libraries, craftsmen die without passing on skills. The explanation is plausible and probably correct for many cases. But it doesn't address why these specific technologies never re-emerged elsewhere. Why didn't other cultures develop bronze astronomical computers after contact with Mediterranean trade? Why didn't electroplating spread once the principle was demonstrated? Why didn't aerodynamic knowledge lead to actual flight experiments? One possibility is that these instruments represent the pinnacle achievements of specialized knowledge systems that didn't translate across cultures. A Greek engineer trained in gear cutting might create an Antikythera mechanism, but lack the mathematical framework to teach others why the gear ratios work. The artifact preserves the achievement, but the understanding dies with the creator. This would explain singular masterpieces without successors. Another possibility is that some technologies were actively suppressed. Ancient sources mention inventors who faced persecution for devices that threatened established interests. Archimedes' war machines terrified Roman forces. His death during Syracuse's capture effectively ended that line of development. Similar suppression could have occurred for other threatening innovations. If an invention challenged religious authority, economic interests, or political stability, removal of the inventor and destruction of the devices would end the technology's spread. But the most unsettling possibility is that these instruments represent inherited knowledge rather than original invention. Suppose ancient engineers worked from technical manuals copied from earlier sources. Suppose they replicated instruments designed by predecessors whose mathematical and scientific understanding exceeded their own. The precision artifacts would exist, they would function, but the builders might not fully comprehend the principles behind their construction. When the source materials were lost or destroyed, the knowledge would vanish despite the artifacts remaining. This scenario has precedent. Medieval European craftsmen built Gothic cathedrals using geometric rules preserved through guild traditions. They could execute the designs with precision but lacked the mathematical proofs underlying the structural principles. When guild systems collapsed, the knowledge was temporarily lost. The cathedrals stood as evidence of capability that succeeding generations couldn't immediately replicate. Ancient precision instruments might represent similar situations, practical knowledge preserved through tradition, lost when transmission chains broke. Consider the implications if even a fraction of these instruments represent inherited rather than invented technology. It would mean human technological history contains gaps, discontinuities, and reversals more severe than currently acknowledged. The progress narrative, primitive to advanced, simple to complex, would be revealed as oversimplified. Some ancient cultures might have possessed knowledge comparable to or exceeding medieval European capability in specific domains. The loss of this knowledge would represent a civilizational catastrophe whose scale we've underestimated. The pattern becomes more disturbing when examining what happened to cultures that produced these instruments. Ancient Greece fell to Roman conquest. Then Roman dissolution scattered Greek technical knowledge. The Library of Alexandria, repository of Hellenistic scientific texts, burned multiple times before final destruction. Whatever technical manuals explained Antikythera mechanism construction were almost certainly kept there. Mesopotamian cuneiform libraries, potentially containing electrochemical knowledge, were destroyed during successive invasions and empire collapses. Mayan codices were systematically burned by Spanish conquistadors determined to eliminate indigenous knowledge systems. In each case, precision instruments survived, while the knowledge systems that created them did not. Metal and stone endure. Papyrus, parchment, and bark paper burn. The archaeological record preserves tools while erasing instruction manuals. This creates a distorted picture where we see the achievements but not the understanding that generated them. It's as if future archaeologists discovered computers but no programming languages or electrical engineering textbooks. The suppression question remains relevant for modern times. How many contemporary precision instruments and technologies face similar threats? Patent systems theoretically preserve technical knowledge, but patents expire, companies dissolve, and proprietary techniques vanish when organizations fail. The digital age promises better preservation, but digital formats become obsolete, storage media degrade, and centralized knowledge repositories remain vulnerable to catastrophic loss. Ancient precision instruments warn us that technological knowledge is fragile. The Antikythera mechanism was unmatched for over a millennium. Zhang Heng's seismoscope remained unique. Egyptian cubit rod precision wasn't recovered until industrial lira manufacturing. These aren't just historical curiosities. They're evidence that human knowledge can regress, that sophisticated capabilities can be lost, and that the assumption of continuous progress may be dangerously naive. The artifacts exist. You can examine them in museums, measure their dimensions, test their functionality. The precision is real, documented, and reproducible. Modern engineers can confirm that these instruments work as described and demonstrate capabilities far beyond what historians assumed possible for their eras. The mystery isn't whether ancient cultures achieved precision. The mystery is how they achieved it, why they stopped, and what other technologies vanished without leaving even these fragmentary traces. What else did ancient civilizations know that we've forgotten? If cultures without computers could calculate planetary positions to modern accuracy, predict eclipses decades in advance, and manufacture instruments with sub-millimeter precision, what else was possible? How many other achievements were erased by conquest, suppressed by authority, or simply lost to the inevitable entropy of human knowledge systems? The 10 instruments examined here represent only what survived. For every Antikythera mechanism discovered, how many similar devices corroded to unrecognizable lumps on the ocean floor? For every surviving cubit rod, how many other precision instruments degraded to dust? The visible artifacts may be outliers, exceptional specimens that happen to be preserved. The true scope of ancient technical capability remains unknown because the evidence is incomplete and the documentation largely destroyed. If these stories raise questions in your mind, if the pattern of precision and loss troubles you, consider subscribing to Investigator Squirrel. There are more buried technologies, more suppressed knowledge, and more historical anomalies waiting to surface. What other ancient capabilities have been erased from history? Share your theories in the comments below.